Thank you, Chantal, for the introduction. And first of all, I would like to thank the organizer for the invitation to give a talk today and also make this talk available online so I can enjoy it during my quarantine. And also thanks Sal and Brian for arranging things for me in the last minute, and also Matt Young to switch talk with me, switch your schedule with me as well. All right, so this talk will be based on two joint work with Xiannan Li, Kaisa Matom, and Maksym Radziw. So my focus will be on Dirichlet L-function. However, I will start with just briefly briefly discussion about moments of Riemann zeta function, and this is something that you've seen in the past couple of days already. All right, so just recall the definition of the moments of Riemann zeta function. And that's here it is. So we know that there's only two known results for this, for the integer moment, and that is the second moment and the fourth moment. And the asymptotic leading term for the second moment is log t, and for the fourth moment is log t to the 4. And for anything higher than that, we already know that the asymptotic formula are unknown, but we do have a good conjecture for it by several people. And the conjecture will be the leading term is gk times ak log t to the k square over k square factorial. And so ak is this arithmetic factor that you've seen, that you see the formula in Sal talk and Alexandra talk yesterday as well. So this is easy to understand, and it comes from sum of dk square n over n. And gk, this is the hard one that still remain unsolved. And so we have the conjecture for this. So Conry and Gauge get G3 to be 42, and Conry and Gonek is G4, get G4 to be 24,024. And this will be two numbers that you will see throughout the talk today. So around the same time, John Keating and Nina Sned get a conjecture for the moment. And this is based on the Dyson and Montgomery discoveries. And so they compute the moment of the eigenvalue of matrix in circular unitary ensemble, and then get exact formula for that. And that's how they derive the conjecture here. And this is the formula for gk. And once you plug k to be 1, 2, 3, 4, and this is, you see that is matched with the known conjecture or the previous results. Right. So there are for people who work on more conjecture and to get it more precise, Conry, Farmer, Keating, Rubinstein, and Sned get asymptotic expansion for the 2k moment, and this includes the lower order terms, and they use the notation of the shifted moment. And so the recipe also apply to moments of other families L functions as well. So Diaconal and Goldfield got the same conjecture, but using multiple Dirichlet series. And recently, Conry and Keating also got the conjecture, but using the long Dirichlet polynomial and divisor correlation. And this can be thought as kind of like a generalized version of Conry, Gonek, and Gauge work. Okay, and before we move on to the moments of Dirichlet L function, I just want to discuss a little bit why it's hard to compute a high moment. So when we compute a moment, usually we will start with the approximate functional equation. So kind of write the L function as in terms of Dirichlet series. And for zeta 1/2 to the I plus it to the k, you get that is the sum of dkm square root m. And when you do the conjugate to square, so that's why you have m over n to the it here. All right, and then you take integration, and then you will pick up two types of terms. The first term is called diagonal term. It's when m equal to n. So that you will get exactly this expression. Okay, and so n is forced to be equal to m, so n can go up to t to the k over 2. And as you can see that when k is 1 and 2, this diagonal term, this whole thing is, the length is actually less than t. So the second and fourth moment, that's why I just pick up just the diagonal terms here. But for anything higher than 2, so that's the off diagonal term, will start contributing here because the sum starting to be too long. Okay, and this is related to the problem on the shifted convolution sum. This is also another hard problem in analytic number theory. And this type of diagonal term are also a main difficulty for high moments for other families of functions. All right, so that's all I want to say about the zeta function. So now I will move on to the Dirichlet L-function. All right. So the Dirichlet L-function is the generalized version of the Riemann zeta function. So for real part of s greater than 1 is defined to be sum of chi n over n to the s. And chi here is a primitive Dirichlet character mod q. All right. So the family of our primitive Dirichlet L function mod q is analogous to the Riemann zeta function when we look at it in the integration over t. And this is also the family that associated to the unitary ensemble. So what we expect for the moment will be basically should behave similarly to the moments of the Riemann zeta function. Okay, and so now we will define the sum notation here before we move on. So I'll throughout the talk, so the sum star will be the sum over all primitive characters mod q, and phi star q will be the number of primitive characters. And the moments of Dirichlet L function will be pretty similar to the Riemann zeta function. So you have sum over all primitive characters instead and divide by 1 over the size of the family phi star q. And the story go the same way. We know only the second and the fourth moment. The second moment, the size is log q, so we just replace t with q here. And for the fourth moment, this is the work by Hibbrow, Sao, and Yang. So Hibbrow get it for almost all q, and Sao can do it for all q, and Yang do it for the prime q, but he also has lower expansion, lower order terms as well. But the leading term here for the fourth moment is, if you can see, is basically pretty much analogous to the Riemann zeta function case. You have log q to the 4, you have the same constant 2 here, that's the G2 that you saw before. And this is arithmetic factor and over 4 factorial. And for anything higher than that, is conjecture to be the leading term is the following. So you have gk, and this is the same gk that you saw in the Riemann zeta function case, arithmetic factor, and this is log q to the k squared. And that's the same order of magnitude as the Riemann zeta function case too. All right. And even though we cannot prove asymptotic formula for this case, we do have good upper bound and lower bound for the Dirichlet L function. For the lower bound case, there are several works on this. So for rational number greater than or equal to 1, so Unixon Sao derived the correct size of lower bound here, q log q k square. And there's an extension of this work by Radziw and Sao for all real k number greater than or equal to 1. And then in my work with Xiannan Li, so we got the rational number between 0 and 1. And then for the real number, so this is from the idea of Winston Heaves and Sao, and then Penkau worked this out explicitly in his paper. For the upper, go up there. For the upper bound, we have for all k, real part of k, real k greater than 0, but this is under generalized Riemann hypothesis. And this is just use the idea from Sao paper, and then Adam Harper that get rid of epsilon. So when Sao got it, so he got the upper bound of psi k squared plus the power is k squared plus epsilon, and Harper result can get rid of that epsilon. All right. So one nice thing about this Dirichlet L function is that, well, you have one average over chi. You can also add an extra average in this family. So you can add the average over Q as well, the conductor here. And if you're familiar with the last if inequality, you see this type of the two average before. That's, chi come from last if inequality. And in fact, Huxley showed that for the 6 and the 8 moment of these two average, he can get the correct size of upper bound and without assuming the generalized Riemann hypothesis here. And here just want to compare these two average. So if you have only one average over primitive character, the conductor is Q. Two average also have the same kind of conductor for this family, but the size of family is different. So if you have one average, you just have the size Q. But two average, you actually consider the bigger size of Dirichlet family, and now the size of family is actually Q square. And when you have like a big size of family with a smaller conductor, so we do hope to get something nice when we talk about the asymptotic formula. And that's what we're gonna do next. So let's start with the leading term for the 6th moment first. So explicitly, so you can just use one of the recipe that you like. So I pick CFKRS. And so the leading term is 42. So that's the G3 number here. And this is arithmetic factor. And then the sign is log Q to the 9. And as I mentioned before, so if we can get a good upper bound for the two average here, can we get asymptotic formula for the 6th moment for this larger family of L function? And it will be good to verify the conjecture. And also, this is the first moment that you see off diagonal come into play. The off diagonal actually contribute to the main term. So it will be good to see this type of structure when we compute this moment. All right. So the pioneering work on this is actually by Conry, Iwaniak, and Sao. So they can obtain the asymptotic formula for this moment. So they still have this two average here, average over Q and average over chi. However, in their work, they need to add one extra average over the critical line. So instead of looking at L1 half chi, so they look at 1L1 half plus IT times chi and multiply by this gamma factor 1 half plus IT here. And the choice of gamma factor is just, to match with L function and in the functional equation. Okay. So it looks different, but it's basically almost the same thing because the integration over T here is pretty short because the gamma function decay really fast along the vertical line. So it's almost the same. So their works, they obtain so they can obtain this leading order, they can obtain the 6th moment now, and the leading term look like this. So you can see that you have 42 come out, and this arithmetic factor is matched with what we saw before. And then you have this log Q to the 9, and you just have the sum come out and the gamma factor come out. Okay, so that's what they have. That's a pretty nice result. So they also state this in a more precise technical result, including shift and with a power saving error term of 5Q squared minus 1/10. And as I mentioned before, the integration over T is pretty short, but getting rid getting rid of it is very challenging because you actually need to deal with things that's called unbalanced sum. And I will explain a little bit later what it means by unbalanced sum. Well, recently, so with my work with Xiannan and Kaisa and Max, so we were able to get rid of this integration over T, and we can obtain the 6 moment without the average, that average over critical line. And we got the the asymptotic formula that we expect. And again, we can state this in more precise technical result, including chips, and we get the power saving error term as well. All right, so any questions so far before I move on? All right, so if not,
there is a question.
Yes.
Yeah, so
I'm sorry.
would one try to restrict to perhaps just like a quadratic character and average over Q? Get rid of one further average?
Sorry, can you repeat that again?
I think you should come here, because I also don't hear well when you say, come here and ask your question here. That would be the case. I also cannot hear you well, so I cannot repeat the question. I'm sorry.
So could one get rid of a further average and just take a quadratic character and average over Q?
Just do quadratic character view. So I actually not sure the answer for that question, but that's something, yeah, we can try as well. Yeah. Sorry, I don't have a good answer for this. Yeah.
Quadratic characters, we don't even know how to do the fourth one.
Yeah. Mm-hmm.
So please continue. Sorry.
All right, thank you. All right, so the technique to derive the result for the Conway-Ibanez and sum here for the 6 moment is actually applied to the higher moment, which is the 8th moment. So that's what I'm going to mention next. So again, with the recipe of CFKRS, you can get the conjecture for the 8th moment, and the leading term look like this. So you have this 24,024 arithmetic factor, and the size is log Q to the 16. And then by kind of follow the same idea to 6 moments. So Xiannan Li and I can derive the asymptotic formula for this last family of L function, but with extra average over T here. And this is assume the generalized Riemann hypothesis. And I will point out later where we actually use this assumption. And then recently we are able to get rid of this generalized Riemann hypothesis and get the result, the correct sign for the leading term here. So however, for this result, we cannot get the lower order term. So the error term that we got is only Q squared log Q to the 15. Okay, so now we're gonna go on to the sketch of the proof. So I will start with the proof of the 8th moment result here. And if I have time, I will talk a little bit about the proof of the 6th moment. All right. So we start with the initial setup for the 6th and the 8th moment. And so with the T average. So this is essentially what we want to consider. So we have sum over chi here, and we just replace the condition Q like around psi big Q as the smooth function here. All right. And again, as I mentioned before, when we want to compute moment, so we want to just do approximate functional equation first, and then we apply the orthogonality relation for Dirichlet character, and this is sum over chi here. And so roughly, so after changing everything, so L1 half plus IT chi kind of come to be dkn here, square root n, mn, and then with all this orthogonality, we have this condition m is n mod r. And then the size of the length of the sum m and n, you can go think of it as you can go up to q to the k over 2. And so when k is 3 is go up to q to the 3 half, and k is 4 is q square. And so in our simple model, the main contribution will come from when d is small. So we just work out the case when d is 1 and I is q to illustrate the idea. And so what happens if we don't have the integration over t? So now the main contribution will be pretty similar, except one condition need to be changed. And that's the condition for the size of m and n. So now it will go up, m times m must go up to q to the k. Okay, so just want you to compare this a little bit. So if we have this integration, m and n go up to q to the k over 2. And if we don't have, m times n go up to q to the k. And that's this integration kind of balance m and n, kind of force them to have the same size. So if m and n have the same size, it can go up to just q to the k over 2. And without it, we need to consider the thing called unbalanced sum. That means one variable can be big and another can be small. So for example, when n is q to the 5 half and n is q to the 1 half. All right. And so the diagonal term is easy. So that is m equal to n. And the hard one is the off-diagonal terms. And we know that we expect to have a main term come from the off-diagonal term as well. So what do we do with off-diagonal term? Well, we know that m is not equal to n. So we can write the condition m is n mod q as m minus n equals to hq. And h is non-zero. And so the sign of h will be m minus n over big Q here. Right. So, and the nice trick from Congruent and Sao is they actually replace the congruence condition mod Q with the congruent condition mod H instead. And what is good about H is that the sign of H is less than Q. So I just want to work this out explicitly for you. So this original sign is big Q and H is this. So for the sixth moment, the critical range that we usually consider is Q to the 3 half. So the sign of H here is Q to the 1 half. So there's a conductor is reduced by quite a bit. However, for the eighth moment, the critical range is Q squared. So when you do complementary divisor trick, it turned out that the sign of H can just still be Q. So this is still the same sign and we don't like that. So one thing that we need to do further for the eighth moment is that we need to truncate the sums over m and n. So if m and n can be a little bit smaller, then h can be a little bit smaller as well. All right. And later I will show you why we actually like when h is small. And if we do not have integration over t with this balanced sum, unbalanced sum, you can see that the size of h can be much larger than q, and this is not good for this technique. Right. So now we need to truncate the sum of m and n first for the eighth moment, and then we can go on to the off-diagonal term. So what we need to show is that we want to show that the tail of the sum is actually pretty small. Okay, so this is what we want to show, that the when m and n is between q square minus epsilon to q square, you get that this original sum here is little o of q square log q to the 16. And this would allow us to consider the shorter sum, which is up to q to the square minus epsilon. And you can think of epsilon to be 1 over log q in this case. And with this, you can see that complementary divisor trick now is less than q. All right. So how do we show this? So this is pretty much just doing a last sieve inequality. And this is the one that we use. So the sign of harmonics. So this is, so if you see in Math Young talk, this is about it. By the sign of harmonic family is r squared and plus the length of the sum and sum of the coefficient a squared. And we apply this into the sum that we want. And so the sign of this harmonic family is q squared here. And the length of the sum can go up to q squared in this case. And this is already balanced. So this is, optimal already. And so, and this is the sum of d4 square n over n. And this is the sign of log q square to the 16. And then subtract with this, the n here. And just doing a little bit of Taylor expansion, you get epsilon out. And that's the proof of this bound. Okay, so that's the truncation. All right, so next, we go on to off-diagonal term. So we want to show that the modulo, so remember that we replace the congruence condition modulo Q with the congruence condition modulo H. And now we're gonna replace this congruence condition modulo H further, and we actually express it in terms of Dirichlet character by using orthogonality relations. And this is roughly what we look at. So if you notice, we have chi, sum over chi here is chi m bar here is chi mod h. So if you apply orthogonality relation, you get back m is n mod h here. And however, we do need to include this just to keep track that where the h come from. So it's come from m minus n equal to hq. So now we will pick up another main term from diagonal terms, and where the main term come from the principal character. So we expect this to be big. This is like another like a L function, like a Riemann zeta function here. And the rest, the principal character, the non-principal character, sorry, will give an error term. All right, so now I will just pretty much focus on the error term here. And that's the technical part that we need to bow. So we start with a very simple model. My simple model is that I just ignore this condition first. M minus n is HQ. Okay. And I just want to illustrate why it's nice to use complementary divisor trick. Okay, so if we don't have complementary divisor trick at all, so what we're gonna do with this error term is that we just sum it in the modulo Q. So by using last sieve inequality, the size of this family is Q squared, and plus the length of the sum is n. And dk n squared over n is log Q to the k squared. So we already see that this is already like as large as the main term. So this is not good when it comes to bound the error term. But if we have the complementary divisor trick, that's good. So the error term is small. So because h is smaller than q, and just a little bit small is good enough because this go up just to q squared minus 2 epsilon. And when we sum the whole thing, this is still little o of q squared. And that is a very simple model of error terms. However, our life is not this simple. So we do have this condition that we need to include. We cannot ignore it. M minus n is HQ. And so when H is small, if we fix n, the sum over m is restricted to an interval that is much shorter than q squared. Q squared, remember, is the size of this function, this L function. So we are dealing with the problem of the sum in short intervals. And that's, you know, that's something that we need, we kind of like stuck for a while when we work on it like in 2014. So in the end, we decided that, okay, let's use generalized Riemann hypothesis, and we can find cancellation in this sum over m and n in this restricted narrow region. All right. And then I gave a talk about this result at MSI in 2017. Kaisa and Max were there. And so they think that they can use the idea from their work, an idea from their work on multiplicative function in short interval. And this is kind of like a same type of problem that they consider. So to get rid of GRH condition, and it's successful. So we are able to get rid of GRH, and that's pretty nice. However, as our discussion progressed, we realized that maybe there's another alternative way to do it, and it's just trying to understand the Mellin transform better, and then we apply functional equation and then hybrid to obtain the same result without GRH. And that's what I'm gonna focus today. That's the method. Right? Any questions so far before I move on?
So up until this point, it's the proof has followed what you did in 2014. Is that right?
Yes. Yes.
Okay. There are no more questions. You can continue.
Thank you. So now we're gonna start with Mellin transform. So we need to express the condition of m minus n is around the site HQ in terms of the integration. And so if you see in our paper, probably, hopefully we can put it on archive at some point in summer. So the integration look more complicated than that, and that's a difficult technical part for us. But to illustrate the idea, this is a simple model of this condition. Okay. So you can express it as the integration of m over m to the it times some Schwarz class function, and the integration of this is the size is n over HQ. The length is n over HQ. All right. So then we include this condition back into the our original sum and rearrange a little bit, so we can write this. Eventually it look like this one. So you have the sum over h and sum over chi mod h here, star primitive character, and then you have this sum of d4m here over m to the 1/2 plus it chi m, and we just put smooth function here. Just say that m is around size big N. And I will write t as n over HQ here. All right. So when you see this two sum and integration, so this is also some sort of last sieve that you can try, and that is hybrid last sieve. So let's try that and see what we get. So the size of the family now is h squared times the integration, which is the length is t, and the length of the sum is n, and it's the sum of the 4n squared over n. And if you see that q squared over n is cancelled with n, and this is log q to the 16, so you still get back q squared log q to the 16, and this is too big because this is the size of the main term. So we don't like that. All right. And we see now that, well, one point that is failed is the length of the sum here is n is the same as n here. So this is, the sum is too long. So what should we do? Well, we apply the functional equation to this sum of D4M. And this is kind of around, this is approximately L to the 4 of 1/2 plus IT chi. And if you prefer Voronoi summation, you can think of it as a Voronoi summation here. And now you change from the sum over n to this sum here. And what is the sum, the size of the sum here? So you need look at the conductor to the 4. So what is the conductor? You have chi m, so that the conductor is h. And you have this integration, so the conductor is t. So the th to the 4. And what is the length of the sum is over n. All right, and we hope that this sum is a little bit shorter than the original sum. And let's see if it's shorter. All right, so we put everything, all this notation in, and it turned out that this is just a little bit shorter than q squared. So it's q squared minus 3 epsilon. And turned out that just a little bit shorter is good enough. So now we plug in, we can apply hybrid Lassif again. And so we put everything in the above, in the bound. So n is, recall that is q squared minus epsilon. And this is the new length. The dual sum length is q squared minus 3 epsilon. And h squared t, since h is a little bit less than q, and you pair with this t, you also get q squared minus 2 epsilon. And this sum, you get log q to the 16. And it turned out that this one has q epsilon, this one has q minus 2 epsilon, and this is q minus 3 epsilon. So we still save q minus epsilon. So it's still little o of q squared. So usually when you see q epsilon, when you try to bound in math, in problem in trigonometry, you can just ignore that and say it's small. But it turned out that for this work, you actually need to keep track this little epsilon along the way to get the correct size of the term. And pretty much, so that's the sketch of the proof of the 8th moment. All right, so any question before I move on to the 6th moment?
No question. That's good.
Thank you. All right, so next will be the 6th moment. So this is the one without the average over t. All right, so just recall from the approximate functional equation, this is approximate of what we need to understand. So now the condition will be m times n up to q to the 3, and m is n mod q. Sorry. And so what we do is that we actually split the range by the dyadic sum into 3 range. The first range is when m and n is small. And what I mean by small, that is that I want to go up to at most q squared minus delta a little bit. And the reason to use this cutoff is because this is the region that the complementary divisor actually work. So because h is less than q in this range, and it turned out that this range gives the main contribution. And for the other range, this is when m or n is big. So when one is big, another one is forced to be small. So I will just, without loss of generality, I will let m to be greater than q squared and n is less than q. And this is supposed to be an error terms. And in this range, we split it into 2 range. The first one is called very unbalanced. And this is when M is really big, Q to the 5/2. And the advantage of when M is really big, we can do apply the functional equation or if you think of it as a Voronoi summation for D3M. And the dual sum turned out to be small, too short. So we can bound the dual sum for this summation here. All right. And the most difficult part of this work is when M is kind of intermediate range. It's between Q squared to Q to the 5/2. And for this intermediate range, we will start with D3M. We don't work on it just D3M. We actually write it as the convolution of the identity 3 times. So we write it as the sum of E, F, G equal to M. And again, we split the range of the this E, F, G into dyadic interval. And without loss of generality, we can just let E to be the longest range. And now the congruence condition will be E, F, G is N mod Q. All right. And and the typical thing for this that you see a couple of times already, we will do some sort of Voronoi Poisson summation, and we take advantage of the longest sum, which is the sum of over E. So it's the longest. So what we do is we hope that the dual sum will be small. So we do the Poisson summation over E here. So now this is the sum that we come out. So everything still look the same, except the length of E now is less than is Q over E instead. And you can see that, let's say when E is like Q to the 5/6, then the length of E is only like Q to the 1/6 here. And we have this exponential term come out, come from this congruent condition here. And with this, and then further we apply reciprocity for this exponential here. And the reason that we apply it because we don't want to deal with the inverse of FG. Okay, so we change it from NEFG bar Q to minus EQ bar over FG instead. And we have this extra term here, but the sign of the sign in the exponent in the last term is pretty small. So this last term can be absorbed into the smooth function. And now after we do reciprocity, we will do Poisson summation in Q. Okay, and once we do Poisson summation twice, so there's a Krusterman sum actually appear. Okay, and it turned out that we have the sum of the Krusterman sum. Okay, and now the critical range that we want to understand is when E is Q over E and R is, this is after the Poisson summation in Q. So the critical range is FG over Q. So FG is the conductor here. And the length of the sum, original sum is Q. So it's FG over Q. Okay. And when you see the sum of Krusterman sum, what do you think of? So the natural one to apply is Kuznetsov formula. And that's what we do. Okay. And so there are two parts of, so after Kuznetsov formula, so there are several parts from that, but really there are like two main things that we need to consider. So the one is the holomorphic, continuous, and regular spectrum. So these are the easier terms to deal with, and we can use spectral Lassiv inequality, for example, in Dirichlet and Iwaniak's work, to bound them. And the hardest part of this whole thing is the exceptional spectrum series. And so after we do some Cauchy inequality, so basically this is the one that is we actually need to understand and bound. Okay, so this is the sum of the level of the form, and lambda j is the exceptional eigenvalue. So it's in terms of 1/4 plus kj squared, and kj is purely imaginary. Okay, and so rho ij here, A is the Fourier coefficients of eigenform associated to lambda j around the cusp A. Right. And you see and then y is just a real number, is called a weight here. And if you see something like harmonic and some square, one thing that you can think of is if there's some sort of Lassiv inequality you can apply, and the answer is yes. There's a work of Dirichlet and Iwaniak, so they have a weight Lassiv inequality available for the exceptional eigenvalue that we can bound this sum. And so there will be two separate cases for this. And so the case when the sum over E tilde here, so E tilde is R times E. So R is the one here and E is here. We combine the term because we have RE over here. All right. So, okay, so if the sum is short, so Lassiv usually nice to a short sum. So you can apply the Lassiv directly and we get the satisfying bound for that. And for example, of the short sum is when when M is the sign on the one end of the range, which is around Q squared. However, when the sum is long, so you see in the egg moment case before that, you will apply functional equation to get the dual sum, and the dual sum is shorter. So then you can apply the Lassiv inequality. Right? And this is kind of applied to the case, for example, in the other end of the range, which is around Q to the 5/2. And so what we use is we actually do the functional equation to the sum over R in this case. And you can see that the original sum here start with Q to the 5/6, and the length of the sum at the end after the dual sum is Q to the 1/3. And then after that, you can apply the weight Lassiv inequalities. Right. And then, so what the hardest part on this slide is the functional equation. And if you see this, rho J1G, basically this is not something that you can apply functional equation right away. You actually need to, do work on this to be able to do functional equation. And so here are some of the tools that we use to work out this result. Is we actually need to choose a scaling matrix for the cusp 1 over G to be a linear operator. So kind of try to change that into associate rho J1 over G with the rho J at infinity. And then this rho J1 over J is not necessarily a new form, so we cannot apply the functional equation. So we also need to write them into the sum of new form, and that's the work of Bromer and Dirichlet that we do. And that's pretty much I want to say about the 6-moment proof. And that's all I want to say today too. All right, thank you very much for listening.
Thank you very much, Phi. So are there any questions? Please try to speak loud. Yes, there's a question of here, yeah.
What about the tense moment?
Oh, for this family, we don't have an idea how to get the 10 moment, but Xiannan and I are working on the gamma 1 QL function. And that's one we got the asymptotic formula for 6 and 8 moment as well. But we think that if we actually, that in that family, you can actually add one extra sum. If you can add one extra sum, and we might be able to get 10 and 12 moment for that family.
You want to ask about the 12th moment now? Yes, Henrik.
Did you try a 6-pi moment asymptotic for modified L-function?
I do not try that. Yeah.
There's a potential.
Yeah, that's a that's a good idea. Yeah.
I have a question. You
Yes.
didn't explain where the magic number for the 8th power, since the complex is around these moment numbers, came in your analysis.
Sorry, I don't understand the question.
You can go to the microphone.
That's it, 24,000. Okay, where did the number, 22, where did the number 24,024 come in your analysis? Does it just add up, or is there some conceptual explanation of it?
There's no conceptual explanation as far as I see. It just add it up and get 24,024.
Okay, thanks.
Yeah.
Are there more questions? So thanks again. I don't know where to go. Thanks again.
Thank you very much.